Welcome back, students. In this video, we're going to look at determining acid strength by just looking at the structure of the acid. This is called qualitative determination of acid strength in comparison to quantitative, because for quantitative, you would use pKa's. Here, we're not going to use pKa's. We're just going to look at the structure of the acid. Let's dive in. The key to determining acid strength is to look at the stability of the conjugate base. Now, the key here is your acid strength depends upon how stable the conjugate base is once the proton has been removed. There's actually two ways to go about determining acid strength. This is the way that I like to use because I think that it's more clear than looking at how easily a proton can be removed. So if your professor uses a different route of deciding how easily a proton can be removed, that's fine. But in my class, my students use this way because I think it gives us the most success. Before we dive into how the heck we're going to figure out if a conjugate base is stable or not, let's talk about our general guidelines that we're going to use. Let's start with two general acids. I'm going to start with HA as one acid, and we're going to compare that to another acid of HY. And our goal is to figure out which acid is going to be stronger. What we do here is we're going to draw the conjugate base of each of these acids. And the conjugate base is just when you take away the proton, the acidic proton that's being removed. Once you've drawn the conjugate base, you look at those conjugate bases, and you're going to use the criteria we're going to talk about next to decide which base is more stable. And the more stable the base, the stronger the acid. So if we decided that Y- was the more stable base, so if this was more stable, that means that HY would be the stronger acid of the pair. And I want to talk about why that is before we get into discussing how to decide if a conjugate base is more stable. And I think that the easiest way to do this is with respect to a real-life example of money. Let's imagine that you are a young person who is paying for college, is paying for your rent, you're paying for your bills, you have a part-time job, and you're still managing to do all of this. And someone comes to you and asks for a donation. They asked for a donation at your favorite charity, a place that you would really like to help. But your dollar, or $50, or however much it is, that's your proton. And your dollar, you just can't give it away right now. Because if you gave your dollar away, then you wouldn't have money for food and you wouldn't have money for rent. So as much as you would like to help that charity, you hang on to that dollar because giving away that dollar puts you in an unstable position. That would be an example of a weak acid. So the dollar is the proton, and we're hanging on to it because if we give it up, we are unstable. Whereas 10 years down the line, you've finished college, you are having a great time in your job where you're making an excess of money, more than you actually need. And the charity comes back and says, "Can you donate?" And you look at your budget and you say, "You know what? I can donate. If I give away this dollar, or if I give away this $50, I will still be stable. I will still be able to pay my rent, pay my bills, and eat. And so, yes, I'm going to give away this dollar." And that's what your strong acids are like. Your strong acids can give away their proton and still be stable once they've given it away. And the stable is the stable conjugate base. So this is the idea behind the fact that acid strength depends upon the stability of the conjugate base. Your acid can only give away its proton if the result is something that is stable. Let's look at the factors that affect the conjugate base's stability. The 4 factors that affect the conjugate base's stability are given here. And what I want to do is go through each of them one by one. First, we're going to look at atom, then we'll look at resonance, then we'll look at induction, and then we'll look at orbitals. We are going to consider these factors in order because it is an order of importance. It's like, please excuse my dear Aunt Sally in algebra class, right? We are going in order where first we look at atom. If atom doesn't help us, we go to resonance. If resonance doesn't help us, we go to induction. If induction doesn't help us, we go to looking at the orbitals. So let's go one by one and look at what factors are going to help us first when we consider the atom. Here I have 2 acids, and the first one doesn't really look like an acid, but that's okay. And I have HF, which does look like an acid. The first step for every one of our pairs of acids that I'm going to give you is to draw the conjugate base. We're going to draw the conjugate base of our first acid, and it actually doesn't matter which proton you take off, right? They're all carbon sp3 to hydrogen protons. You could take off one at the end or one in the middle. And then for HF, you're going to take off the H and get F minus. Now what you do is you ask yourself, which atom has that extra electron density? Which atom has the negative charge? And once you figure out which atom bears the negative charge, you assess the periodic table to figure out if the atoms are in the same column or the same row on the periodic table. Because if they're in the same column, we consider one thing. If they're in the same row, we consider something different. So these are in the same row, and that's what we're going to look at now. If the atoms are in the same row, what helps us decide whether or not an atom is able to stabilize extra electron density when it turns into an ion is electronegativity. Here, this extra electron density is on a carbon. Here, the extra electron density is on a fluorine. So we look at the electronegativity values. Fluorine is significantly more electronegative than carbon, so fluorine can better stabilize the excess electron density. So fluorine is the more stable base. And remember what we said, that the more stable the base, the stronger the corresponding acid. So this means that HF is the stronger acid. Some of you might be pausing and thinking, wait, in general chemistry, you told me HF isn't a strong acid. You're right. In general chemistry, your teacher either gave you a list of 6 or 7 strong acids, depending upon what they thought was a strong acid. HF did not make the cut. The key here is that acid strength is relative. So in this pair, HF is the stronger acid. Is HF a strong acid in general chemistry? No, it is not. But out of this set, HF is the stronger of the 2. Let's look at another example of a pair of conjugate bases where the 2 conjugate bases are in the same column instead of the same row. Now, HF gave rise to the conjugate base of F minus. HI gave rise to the conjugate base of I minus. When we look at these 2, we see that we're comparing fluoride ion to iodide ion, and these atoms are in the same column. They're not in the same row. When we consider atoms that are in the same column, we're looking at size. Remember that when you go down a column in the periodic table, that the trend is that the size increases. Fluorine is thus smaller than iodine. Iodide can take on that extra electron density more easily because it's bigger. So bigger atoms or ions can better stabilize the charge. So bigger ions are more stable. That means that iodide ion is the more stable base out of this pair. And because iodide ion is the more stable base out of this pair, HI is the stronger acid. Now, what if you draw the conjugate base and the extra electron density is on the same atom? What would you do then? Well, that's what we're going to do next. If we draw the conjugate base and the excess electron density is on the same atom, then clearly this does not help you. So you have to go to the next criteria. The next criteria is resonance. When I look at these two structures, I see that I have an H here and an H here that are on oxygens. I know that those are going to be my more acidic protons than the hydrogens here, 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 and here. Why? Because we just learned that atoms that are more electronegative can better stabilize the excess unnegative charge. So the places that I've highlighted in blue, those protons aren't even going to come off. If we also take into consideration some pKa stuff, remember that for pKa's, your carbon sp3 to hydrogens, those have a pK of 50. That's just ridiculous. That's not really considered an acid. So we look at these two, and I want to draw the conjugate base. So I'm just going to take off the highlighted hydrogen for both of them and put a lone pair in its place. And now we can pause and ask ourselves, where is the excess electron density? Well, the excess electron density is on an oxygen here and an oxygen here. That means atom doesn't help. The excess electron density is on an oxygen in each instance. What do we do now? We look at resonance. When we consider this first structure, the lone pair is localized. It lives solely on that oxygen. Whereas for our second structure, we can draw a pair of resonance structures. And when we draw this pair of resonance structures, we see very clearly that we have a delocalized pair of electrons. Delocalization is a stabilizing effect. When you share those electrons over several atoms, that makes that structure more stable. So which one is more stable? This one is more stable. Why? Because the conjugate base can participate in resonance. And when we participate in resonance, that's called delocalization, which is a stabilizing effect. Because we can have the second conjugate base participate in resonance, that means the acid that it came from is the stronger of the two. So this one is the stronger acid of this pair. So we started with atom, we looked at resonance. Now, what if resonance doesn't help us? Let's look at an example where that would occur. Here I have two carboxylic acids. I have a hydrogen here, and I have a hydrogen here. These are my acidic protons of these two molecules. Remember, the first thing you want to do is draw your conjugate base. So I'm going to draw the conjugate base where I'm going to remove the proton and put a lone pair in its place. Now let's assess which one of these conjugate bases is more stable. I see that my extra electron density is on oxygen, and over here, again, extra electron density is on oxygen. That means atom doesn't help us. We have electron density on the same atom, so we can't use that. Next, we go to resonance. They have the same resonance structures, so that doesn't help us either. And then we start to ask, how do we decide? Well, that's where induction comes in. Remember, induction is when an electronegative atom nearby pulls electron density toward itself. And that's what the chlorine is doing in the second structure. The chlorine is pulling just a little bit of electron density away from that oxygen and taking on that electron density onto itself. And when we see this chlorine doing this very little bit of help, keep in mind that induction dies off the further away you get. So it matters that the chlorine is close. When I consider these two, the chlorine is making all the difference in the world. The chlorine is creating a situation where this base is more stable because that chlorine is pulling electron density off of the oxygens and onto itself. What you might be seeing now is a trend. When we're looking at something like resonance and we're looking at something like induction, what's happening is there's a stabilizing effect associated with more atoms sharing the extra electron density. This always makes me think of carrying something heavy. So imagine that you are tasked with carrying a heavy box upstairs. And this heavy box is just 50 pounds. It's a big, heavy box. And maybe you struggle carrying that box by yourself. But a friend sees you and comes over and helps, and it gets easier. And then a third friend comes over and helps, and it gets easier. So as we take that extra electron density and we spread it out over more atoms, that stabilizes the structure. Just like how you carrying a load by yourself is not as stable as you sharing that load with friends. Therefore, this structure with the chlorine, even though that chlorine isn't doing as much as something like resonance would, it's doing enough to make this conjugate base more stable than the one that doesn't have chlorine. And therefore, we see that the one with the chlorine is the stronger acid. Let's look at our last criteria, and this is orbitals. When we go through atom, resonance, induction, and there's no difference in where the lone pair and the extra electron density is for those three criteria, our last thing to consider is orbitals. I want to look at an alkene and an alkyne. For your alkene, you have 2 protons here, and your alkyne, you have 1 proton here. If we pull off the protons that I've highlighted in yellow, what we end up getting is a lone pair on this sp2 hybridized carbon versus a lone pair on this sp hybridized carbon. So we have sp2 and we have sp hybridization here. And keep in mind that when we identify what the hybridization is for that atom, that is also the hybrid orbital that that lone pair lives in. So on the earlier page, we already said that this lone pair lives in an sp2 hybridized orbital, and this lives on an sp hybridized orbital. So why the heck are orbitals going to help? Well, if we look back into general chemistry and earlier this semester, we saw that the shapes of orbitals are different. This is a rendition of an sp3 hybrid orbital. This is sp2, and this is sp. And notice how the sp3 hybrid orbital that has more p in it, more p character, is longer and thinner. Whereas the sp hybrid orbital, which has more s character and is 50% s and 50% p, is shorter and stubbier. Why would this matter? Well, what's happening is your lone pair is living in one of these orbitals. The orbital that the lone pair is in is the orbital for a carbon, and that carbon has protons. And negatives and positives like one another. And the closer the positive and the negative can be, the more stable a situation you're going to have. So the electrons in an sp versus an sp2 hybrid orbital are going to have a difference in their stability. When we consider the sp hybrid orbital, this shorter and stubbier orbital is going to result in having the lone pair closer to carbon's nucleus that contains a positive charge. And that's going to stabilize that lone pair. So let's write that down. The lone pair in an sp hybrid orbital is closer to the protons in the nucleus of carbon, because we're looking at carbon right now. And when you have a positive and a negative close to one another, that results in something that's more stable. So the lone pairs in an sp hybrid orbital is closer to the protons in the nucleus of carbon, and that distance, when there's less distance between the protons and the electrons, that creates stability. Therefore, what we find is lone pairs that are in sp hybrid orbitals are more stable than lone pairs in sp2 hybrid orbitals, which are more stable than lone pairs in sp3 hybrid orbitals. So we see that this structure of the set is the stronger acid. Now, if we wanted to just compare pKa's really quick to help see that even though it might not feel like this matters very much, that it actually really does, if we go back really quick and just say this acid versus this acid and compare the pKa's, the pKa of this one is something like 44, and the pKa of this is 25. That's a huge difference, because remember that the pKa is a log scale. So you're seeing a 10 to the 19th power difference in acid strength between these two, just because of the placement of the electrons with respect to the protons. Now I want to do an exercise. I have 3 pairs of acids here, and I want you to take the time to figure out which acid is stronger in each pair. And if you could write down a sentence as to why, when you explain things, that really helps solidify it in your mind. And it also helps you recognize if you don't understand something. So why don't you take a moment, pause me, and figure out which of these is going to be the stronger acid. All right, let's compare some answers. So for the first pair, I want you to say that this one is your stronger acid. Specifically, this proton is going to be your acidic proton, and this proton here would be your acidic proton. But the first structure is the stronger acid because you have a chlorine there. Now, notice how the chlorine is further away. That's fine. It's still going to have an impact. It's just not going to have quite the same impact if the chlorine was closer. For the second one, this proton and this proton are your 2 acidic protons. The first structure, again, is going to be your stronger acid, because once you draw the conjugate base for that, you can see that the lone pair is in resonance with the aromatic ring. So what we can do is start drawing resonance structures like this. And that's just how you would generate the first one. There's plenty more. For the final pair, your iodine, your HI, is going to be the stronger acid, because if you compare iodide versus bromide, iodide is further down in the column on the periodic table. So for this one, you were looking at atom, and you were seeing that iodide is bigger and thus better able to stabilize the charge. So if we just kind of go back and say this one, we looked at induction, the second one we looked at resonance, and the third one we looked at atom. Let's try another exercise. For this exercise, I have one structure, but I've specifically drawn out 2 hydrogens on both structures. I'm also going to highlight them so you know which ones I'm talking about. So this one and this one, this one and this one, and this one and this one. I want you to look at the 2 highlighted structures in each molecule, the 2 highlighted protons in each molecule, and tell which one is going to be the more acidic proton and why. So pause me and give yourself a moment to do that. So let's look at the first one together. For the first one, if you would have taken off this proton, the lone pair would be on a carbon. If you take off this proton, the lone pair would be on an oxygen. In that case, your lone pair is on 2 different atoms. What you need to do is start with atom and decide where are those 2 atoms with respect to one another on the periodic table, and they are in the same row. Because they're in the same row, we look at electronegativity. Oxygen is more electronegative than carbon, and therefore you're going to see this proton be the more acidic of the 2. Let's look at the next one. For the next structure, if we would have taken off this proton that I just boxed in blue, you would have a lone pair on a carbon. If we take off this proton that I boxed in green, you would have a lone pair on a carbon. So atom doesn't do you any good. Now let's look at resonance. You might need to actually draw out the conjugate base and not just do it in your head if you're trying to figure out resonance. So if we put the lone pair here, notice how then we can draw this resonance structure. Whereas if our lone pair was all the way at the end of the structure, there's no way that thing's in resonance. It's too far away. You need to be adjacent to a pi bond in order for that to be in resonance. So this one has no resonance, and thus that lone pair is localized. This one experiences resonance, so that lone pair is delocalized. Delocalization is a stabilizing effect, which therefore makes this negative charge or a pair of electrons more stable. So the more stable the base, the stronger the acid. So I've highlighted our stronger, more acidic proton in blue. Then for our final structure, I have our 2 protons that are highlighted. The first one on the left, if you take that one off, your lone pair is on oxygen. On the right, if you take off that one, your lone pair is still on oxygen. And if we look at what's connected, we have the same functional groups connected. They're both part of a carboxylic acid, so they experience resonance. What's different is this fluorine nearby. That fluorine is closer to the hydrogen on the left, and that fluorine is going to participate in the inductive effect. It's going to pull electron density toward itself and stabilize the lone pair on the oxygen. This makes for our hydrogen on the left to be the more acidic proton. Let's wrap up. In this video, we looked at conjugate base stability, looking at the 4 factors that need to be considered in order. We want to make sure that we can look at a pair of structures and decide which one is more acidic. And we also want to be able to look within a structure and figure out what is the most acidic proton within that structure. It's going to take a boatload of practice, so keep working on it. As always, thanks for your attention. This is Katoni signing out.